Okay, so let's take a look at this. What we have here, this is an organic compound called aniline. At each corner of this hexagon there is a carbon, and 5 of them have a hydrogen on that carbon, and you can see that the bonds between the carbons alternate with single and double bonds. That's something by itself that's called a benzene ring. But when we put an amine group on it, which is a nitrogen with 2 hydrogens, we get a new compound called aniline. The nitrogen has an unshared pair of electrons in it, like ammonia would, which can react with an acid like hydrochloric. The unshared pair is able to be donated, so aniline is a base, like ammonia is. The result is that the hydrogen leaves chlorine with a positive charge and bonds to the unshared pair on the nitrogen, giving us this, NH3+, and the negative chloride. So this, having 2 separate species with opposite charges, this is technically a type of salt. Now these organic amine-based salts like aniline are named a little bit bizarrely compared to what we've seen so far. Normally you would see this called aniline hydrochloride. I have tried to keep you from saying hydrochloride throughout most of the year, but here's where it actually applies. This could alternately be called anilinium chloride. So the problem here is a question of finding the pH of a 0.233 molar solution of aniline hydrochloride or anilinium chloride. So the action here is going to be that this anilinium, which is the conjugate acid of aniline, is going to act like an acid. All right, so I'm going to write it this way. We've got 6 carbons, 5 hydrogens, and NH3 that is positively charged. Okay, so that is this thing, anilinium. That will react with water by giving one of these 3 hydrogens, the positive one, to the water so that we get hydronium, and we get aniline, C6H5NH2. We're producing hydronium, so it's acting like an acid. Now if this stuff is 0.233 molar, then initially we have that. We have no hydronium, no aniline. This will decrease by X as our change, and we will create X of each of these, so that at equilibrium we'll have 0.233 minus X, X of hydronium, and X of aniline. Now what we need is we need the Ka for anilinium. The problem is, because this is a conjugate of a base, we're not going to find Ka for this in any of the tables. So we need to remember that for a pair of conjugates, Ka times Kb equals Kw. Because we can find, here's the conjugate acid, by giving the proton to water, this turns into or is left as the conjugate base. And we can find a Kb for this conjugate base. We would look it up in a table in the appendix of the book, and it turns out that Kb for aniline is 4.6 times 10 to the negative 10. Kb is 4.6 times 10 to the negative 10. If we multiply that times Ka, we will get Kw. And I hope you remember, Kw is constantly 1 times 10 to the negative 14. So we'll divide each side by the 4.6 times 10 to the minus 10, isolating the Ka over here on the left, And this divided by this, well, let's find out. Let's see, 1 times 10 to the 14 negative, helps me turn it on, doesn't it? 1 times 10 to the 14 negative, divided by 4.6 times 10 to the 10 negative equals, and let's get that into scientific notation, 2.17 times 10 to the minus 5. 2.17 times 10 to the minus 5. So now we can use that over here. Our Ka for this acid, which is anilinium, the conjugate acid of aniline, which is the conjugate base whose Kb we found over here. This Ka is going to equal 2.17 times 10 to the minus 5. And it's going to equal X of hydronium times X of aniline over 0.233 minus X of anilinium. And since this number is pretty small, we should be safe to disregard this. And that means that we're going to take this number and multiply it by this number. We're going to multiply both sides of the equal sign by this 0.233. I've left that number in the calculator. I'm just going to leave it with all of its digits. Say times 0.233. Now this number, 5.065 blah blah blah, equals x squared. Okay, so now I'll take the square root of that. And that's going to tell me that x is equal to 2.25 times 10 to the negative third. Now what did this x represent? X was this or this, and x was hydronium. So if we do the negative log of this number, log, we get a negative number, do the negative of it, and we get pH equals 2.65. Okay. Let's see, do I want to do another problem on this same video or move to another one? Let me say this about this problem. What we were dealing with here was a salt. Okay? And we just found the pH of a salt, given its molarity. And what we had to do was consider that this was a weak base. We know it's a weak base because it's got a Ka value that's pretty small. And it's reacting with a strong acid, and we know that the strong acid just because we know hydrochloric is strong. So we know that the salt is going to be an acid salt because the strong acid's going to win over the weak base. So we should have and did get a pH that is low, an acidic pH. So there's a problem involving finding pH of a salt. All right, let's talk about buffers and do a simple buffer problem. First of all, buffers are compounds that will resist a change of pH, resist delta pH. They are made by combining a weak acid with its conjugate base or a weak base with its conjugate acid. And that conjugate will be in the form of a salt. So let's consider a buffer that is 0.1 molar acetic acid and 0.1 molar sodium acetate. Now sodium acetate is a salt and it contains the conjugate base acetate. That's the conjugate base of acetic acid. All right, so let's look at what would happen here. Acetic acid, I'm going to write it perhaps a little differently than what you've been used to. We have written it nearly all year this way. HC2H3O2. So to avoid confusion, I can write it that way. Hydrogen and acetate. In organic chemistry, it's usually written this way, or CH3CO2H. Anyway, that's going to react with water to produce, acid. It's going to give this hydrogen to the water, which will turn the water into hydronium. And it's going to leave behind all the rest of this, which is CH3COO negative. So this is acetic acid. This is acetate, its conjugate base. All right, so there's the reaction. Initially, the acetic acid is 0.1 molar. And water doesn't really matter. Hydronium, we would assume that there is none, but we're not going to assume that there is zero acetate because this buffer has 0.1 molar sodium acetate in it. When the sodium acetate dissolves in the water and separates, you'll get 0.1 molar sodium, which doesn't really matter. That'll be a spectator ion. But what does matter is that we will get 0.1 molar acetate. So this is also 0.1 molar. So the change happens. For the acid to ionize and give these protons to the water, the concentration must go down, which means this concentration comes up, and so does this one. Ones, 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 and all the coefficients, so nothing but x's, no 2x's or 3x's. At equilibrium, we'll have 0.1 minus x, we'll have x, and we'll have 0.1 plus x. The Ka for acetic acid is, I believe it's 1.7, depending on the textbook you look at, and I've used several different texts over the years. They'll say anywhere from 1.7 to 1.8 times 10 to the minus 5. This particular example I'm looking at here calls it 1.8, so I'll go with that. 1.8 times 10 to the minus 5. Now that's going to equal x for the hydronium times the other product, 0.1 plus x over 0.1 minus x. Okay. So what do you think about adding x and subtracting x when our equilibrium constant is so small? That's not going to be important. So we can cancel these 0.1s out, right? And that tells us that x is simply 1.8 times 5. Now what did x represent? X represented the hydronium ion concentration. So if we take the negative log of the hydronium ion concentration, which is this, the negative log of 1.8 times 10 to the negative 5 is 4.74. Okay. Now, there's our pH. But let's look at another aspect to this. When we took the negative log of 1.8 times 10 to the minus 5, because it was the hydronium ion concentration, we were also taking the negative log of Ka. And the negative log of Ka is called pKa. So 4.74 is not only the pH of this particular example. 4.74 is also the pKa of acetic acid. So that brings up something we've seen before, and that is the Henderson Hasselbalch equation, which says that the pH of a buffer, equals the pKa of the acid in that buffer plus the log of the base to acid ratio. All right? So the pKa we just found out right here is 4.74. Now, sorry, that's my cat. What is the molarity of the base in this problem? It's 0.1 molar. The acetate is the conjugate base, and it's 0.1 molar. What is the molarity of the acid in this buffer? It's the acetic acid. It's 0.1. So base over acid is 0.1 over 0.1. That fraction is equal to 1. What is the log of 1? It's 0. So we're saying 4.74 plus 0. So what does that give us? pH is 4.74. We already knew that. What I've just shown you is there are two different ways to do this. You can use an ice table and get 4.74, or you can use the Henderson-Hasselbalch equation. Since we were working on a buffer, you find the pKa by taking the negative log of the Ka, and then you would add the log of this fraction that has the base molarity over the acid molarity. Let's put those in square brackets, because square brackets mean molarity. Okay, that was 0.1 over 0.1. And the log of 0.1 over 0.1 is 0. Okay, so there's a little review of buffers and the Henderson-Hasselbalch equation.